And I'm Stan. I'm from the University of Cambridge, and today I'm going to present my recent work regarding sensor calibration fingerprinting for smartphones. And this is a joint work with my supervisor, Alistair Beresford and Ian Sherrod from the Polymath. So what is device fingerprinting? Well, device fingerprinting is a technique to generate a unique identifier, or sometimes called a fingerprint of a device. It has many use cases. For example, it has been used to protect against identity theft and credit card fraud. However, it's more often used by advertisers to monitor your activities and to study your personal interests. For example, I'm sure many of you had the experience of finding that right after you search something in a shopping app, and the relevant advertisement just pops up in some random website. And that's device fingerprinting. If you think of the use case of the whistleblower, then the consequences is even more severe, because the attackers in this case could simply buy or inject some advertisement on the news website, and this could help them uncover the identity of the whistleblower. So to protect against the device fingerprinting, both iOS and Android have deployed a set of countermeasures. For example, on iOS, the developers have no access to your phone number or the MAC address of the hardware modules. While on Android, this is enforced by permission-based access control. Nevertheless, there is a major piece that has been neglected in the countermeasures, and that is the motion sensors. So modern smartphones typically include a set of motion sensors, including the accelerometer, which measures the acceleration of the device, the gyroscope, which measures the rotation of the device, and the magnetometer, which measures the magnetic field around the device. Data from these sensors can be accessed by developers from either a mobile app or from a mobile website, and it does not require any user permissions or user interactions. We find that this is pretty dangerous, because we have proposed a new type of device fingerprinting attack, which we call the calibration fingerprinting attack. So this attack works by inferring the calibration data of these sensors by simply analyzing the sensor outputs, which does not require any permission. And furthermore, we can use the calibration data because normally, if they do calibration, it's most likely to be per device calibration. And we can use this data to uniquely fingerprint every device. We found this attack extremely efficient and effective. The whole attack takes less than 1 second. And as I said earlier, it can be launched from either a website or an app. And it can actually generate a globally unique identifier, even for the homogeneous devices such as the iPhones or iPads. And here's a demo of the attack. So here we have two iPhone XS devices on the desk. And this website generates the calibration fingerprint of the gyroscope for each device. As you can see here, these two iPhone XS devices have a different fingerprint, which is a 3x3 matrix. So how does this attack work? Well, the motion sensors are suffering from different types of deterministic errors, or often called the systematic errors due to manufacturing imperfections. And this is inevitable. And in general, these errors can be classified into 3 categories. The scale error, which means the axis of the sensors is different from the design. And the non-orthogonality, which means the axis of the sensors are not perpendicular to each other. And also the bias, which means the reference point of the sensor is different from the nominal value. Good sensor accuracy is often crucial, and therefore, some manufacturers may choose to do factory calibration to compensate for these types of errors. In particular, 3 different types of calibration matrices would be calculated. And the format of these matrices is shown on this slide, and each of them corresponds to the type of error on the left. And during the factory calibration, after the manufacturer got these matrices, they would bake this data into the non-volatile memory of the device. and this data will not be changed afterwards, which means it's consistent over time. In general, motion sensors would first convert the analog environmental measurement to a digital value through a component called the analog to digital converter. And then these calibration matrices would be applied to the ADC outputs to generate the accurate sensor readings using the formula here. And the formula up there can be further simplified to the formula down below. And the objective of our attack is quite straightforward, because we know the sensor output, which is the matrix O here. And our objective is to recover the value of the gain matrix G. Here is how the attack works. We first collect a few data samples from the sensor. Then, by subtracting the consecutive sensor measurements, we can effectively remove the bias from this equation. And eventually, we can get the formula down below, which is delta O equals to the gain matrix G times the matrix delta A. However, we still only know the value of delta O, which is the difference between the sensor outputs. And normally, it would be impractical to infer the value of the gain matrix G here because we don't know what the delta A would be. But there are some nice properties we can exploit here. First of all, we know that the output of the ADC can only be an integer, which means that the matrix delta A here only has integer values. And we also know that the gain matrix here is close to its nominal value, which means the value that the sensor is designed to operate at. And this value is often documented in the datasheet. And these properties allows us to infer the value of delta A and further estimate the value of the gain matrix G here. So here is an example. This graph shows the gyroscope output from two devices, the Samsung Galaxy S8 and the iPhone X. One thing you can notice here is that there is a clear quantization on the sensor output, and this is because the ADC values are integers. If we subtract the sensor outputs, as we talked earlier, then we can get a figure here. If a sensor is not factory calibrated, then all the values within a single quantile would be the same value. And this is the case for the Samsung Galaxy S8. But for the iPhone X, you can clearly notice that there is a strong fluctuation in the quantile between the two black dashed lines. And this is a proof that the gyroscope in the iPhone X is factory calibrated. Furthermore, thanks to the clear quantization, we can also know the value of delta A for each data point by simply observing which quantile this point lies in. And in many cases, we don't really know the nominal value of the gain matrix because, especially for iOS devices, the datasheet is not available to the public. But it's not a big issue because we can still estimate the value of the nominal gain using the distance between the adjacent quantiles, as shown on this slide. And this diagram illustrates the major steps to recover the value of the gain matrix and to further generate the calibration fingerprint. So the calibration fingerprint is just another representation of the gain matrix based on the device model, because we found that different device models use different representations of this gain matrix. And we already talked through the first three steps, which allows us to recover the value of the ADC. And once we have the value of the delta A, and we know delta O, and then the linear algebra would allow us to estimate the value of the matrix, the gain matrix G here. In practice, we found that in order to pull off this attack, you only need around 100 data samples, which you can easily collect within 1 second. You may also notice that here we have an improved approach, and this approach, the improved method, ensures that even if the device is under intense movement, for example, if you are shaking your device, this algorithm can still generate the fingerprint quickly and reliably. So just to refresh the memory, this is the gyroscope calibration fingerprint in the previous demo. Apart from the gyroscope, we found that the magnetometer in iOS devices is also factory calibrated. But different from the gyroscope, the magnetometer, the calibration behavior in the magnetometer is more different across different device models. For example, you can clearly notice that there's stronger fluctuation in the iPhone XS Max than the one for the iPhone 5S. But nevertheless, our approach is applicable for all iOS device models and can generate the fingerprint reliably. Furthermore, we also found that the Google Pixel 2 and Pixel 3, the accelerometer is also factory calibrated and can also be fingerprinting using the same approach. We define the SensorID as a collection of distinctive sensor calibration fingerprints, which means for iOS devices, this includes both the gyro ID and the Mac ID. And for Google Pixel devices, it includes the AC ID. And here is how these IDs look like. One thing you can clearly notice here is that the AC ID looks quite different from the other two. And the reason for that is we found that in Google Pixel 3, they actually mapped the calibration parameters to a local file system. So if you have the root access of your device, of your Android device, then you can actually read out these calibration parameters from these files. And this serves as a ground truth for our approach because we compare the gain matrix we estimated with the measurements written in this file, and they're exactly the same. So now that we know that we can generate the SensorID, the next important question is, how unique is this fingerprint? To answer this question, we compared our approach with another fingerprinting framework called the Fingerprint JS2, which utilizes a set of traditional browser fingerprinting techniques, including the canvas fingerprinting. So here, the group size means the number of devices sharing the same fingerprint. So for example, as you can see for the Fingerprint JS2, 45 out of 870 devices have the same fingerprint. And another 36 of them has another fingerprint. But all devices have the unique gyro ID. And this proves that both the gyro ID and the Mac ID has more entropy than the Fingerprint JS2, which stands for traditional browser fingerprinting techniques. And to quantitatively analyzing the entropy of the SensorID, we collected sensor data from 870 iOS devices via crowdsourcing platforms. To ensure that we didn't overestimate the entropy of the SensorID, we also studied whether there are some correlations between the values in the SensorID. And the answer is yes, they do have some strong correlations. As shown on this slide, so basically, the graph shows that the relationship between every two values in the gyro ID here. And if the scatter plot appears to be a straight line, it means that there is a strong correlation between those two values. So in this figure, I marked this strong correlated pairs in red. And for this strong correlated pairs, we deleted one of them in the entropy calculation to avoid the overestimation of the entropy. And as a result, we estimate that the gyro ID itself has around 42 bits of entropy, and the Mac ID has around 25 bits of entropy. But this is for the iPhone 6s model, because this is the most popular device model we have in our data set. So what does this entropy mean? It basically means that the chance of you having two iPhone 6s devices sharing the same fingerprint is pretty low, as you can see here, indicating that this is a globally unique fingerprint. Oh, sorry. And to mitigate this attack, we proposed two options. The first option is to add noise to the ADC outputs. This could help to obfuscate the quantization. And the second option is to run the sensor outputs to the multiple of the nominal gain. And this would remove the fluctuation we saw earlier in the graph. But there is always the third option here, which is the most secure option among the three, that is to remove the access to the motion sensor at once. And so we reported this issue to Apple last year. And Apple, in the recent release of the iOS 12.2, Apple adopted our first option, which added noise to the sensor outputs. And they further removed the sensor access in mobile Safari by default. However, this is currently not implemented in WebKit, which means the sensor data is still accessible in iOS, Chrome, or Firefox, in other browsers in general. And we also reported this issue to Google last year in December. And so far, they haven't fixed this vulnerability yet. So if you have a Pixel devices, the attacker can still fingerprint you using this approach. So to conclude, we have proposed a new type of device fingerprinting attack called the calibration fingerprinting attack that can track users across apps and websites and is extremely efficient and effective. And I think the highlight of this attack is that we highlighted that, so normally the calibration pattern is not something that you would normally consider as a privacy concern because it's basically a trade-off between utility and privacy. But we highlighted that this actually is also a major source that exposes a lot of the personal information. And we show that this attack is extremely efficient because it can uniquely fingerprint sandbox and homogeneous devices such as iPhone and iPads. And if you're interested in this work, you can find more details on our website, sensorid.cl.cam.act.uk. And if you are running an iOS version that is below 12.2, you can actually find out what your gyroscope fingerprint looks like on our website, because there's a proof of concept implemented in JavaScript to do that. OK? Thanks a lot for the talk. Thanks a lot for coming.
We have time for a couple questions, if folks can line up at the mics.
Thank you for the interesting talk. My name is Ala El-Momani. I'm from Ulm University in Germany. Regarding your countermeasures, you have option 1, 2, 3.
Yep.
I didn't get the difference between option 1 and option 2. Isn't it, scientifically speaking, the same to add noise or to round the sensor output?
So both of them are not like completely secure because you can still do this attack using probability like attacks.
Yeah, I totally agree with you. That
yeah, but I don't have like quantitative like analysis about which one of them is more secure because especially for the first option, it really depends on which noise you are adding to the ADC. For example, we proposed adding a uniform distributed noise, but it's more secure to add like Gaussian noise to the outputs. And that in that way, the effectiveness of the first option is like differs a lot depending on the noise you are adding.
OK, thank you. Yeah.
Thank you.
Any other questions? So one question I have is, this seems to pop up a lot as mobile phones have tons of sensors available on them. Do you think there's a general purpose strategy to solving this, or do you think you have to do something unique for each of these cases?
You mean for other sensors?
Yeah, or like all the different measurements you can collect from your phone. It seems like fingerprinting is a huge problem.
Yeah, so this approach is not just restricted to motion sensors. There are other sensors that I know you can basically fingerprint using the similar approach.
So do you think it's just a function of being able to identify wherever this might crop up, or do you think there's a more elegant solution to like stopping this before you have to write another paper on the next sensor?
I don't think I will write another paper of another sensor if that approach is similar. But if the calibration behavior is different from the model that we used here, then I might, yeah.
All right, cool. Well, thank the speaker again.
Thank you.